please take the away.
Yeah, I'm certainly ready. Thanks for having me. I really appreciate y'all putting on this conference and including me on the program. I'm Alex Moehring, assistant professor at Purdue. This project is joint with Nikhil Agarwal and Alex Politsky at MIT. They're called Designing Human AI Collaboration and Sufficient-Statistic Approaches. So to motivate this exercise, I want to highlight there's been a lot of interest in understanding how AI tools are going to impact human decision makers. This includes questions like, do human AI collaborations improve performance over either modality alone? Do humans effectively use AI tools? And ultimately, how should we think about designing human AI collaborations to maximize the performance of the human AI team? And it's going to be this last question that we're going to try to make some progress on in today's talk. Specifically, we'll be thinking about classification problems. So this is all going to be supervised, good old-fashioned machine learning, perhaps a little bit less relevant to some of the generative AI applications that we've seen. But we'll be thinking about a design space that allows a designer, just to be concrete, you can think about a designer as a firm designing an AI tool for its employees. Or in the case of our paper, it's going to be us, the experimenter, designing an AI tool for experimental participants. And we're going to give the designer a couple different levers. So the designer is going to observe the AI signal. They can then choose as a function of the AI signal to follow the recommendation implied by that signal, so they can automate the cases. Or they can delegate the case to a human decision maker. If they delegate the case to a human, they get to pick what, if any, information about the AI signal that they observe they want to reveal to the human decision maker. We're going to call that a disclosure policy. So like at one extreme, you can imagine full disclosure, where we just tell the human the signal that we observe. So there's like a 75% chance this case is true, for example, or positive, I should say. At another extreme, we could not reveal anything about the AI, so we could just fully withhold our information and not send any signal, just essentially reveal a prior distribution of cases. So importantly, this is a hard problem. There are a couple of different approaches one could think about to try and make some progress on this problem. One approach you could think about is a experimental approach where we run a bunch of experiments, varying our automation and disclosure policies, pick the policy that works the best and run with it. This is, of course, costly because we have to run a bunch of experiments, but also without some sort of strong theoretical guidance, we have no guarantee that we're going to converge on any sort of optimal policy. At the other extreme, we could think about a structural approach where we write down a fully specified model of human behavior and belief updating, estimate the parameters of such a model. And once we estimate those parameters, we could then predict performance of counterfactual automation and disclosure policies. This approach will work, but we'll have to make some strong assumptions. Importantly, we'll have to take a stance on how humans combine their own private information with that of the AI. So are humans Bayesian? Probably not. How do they differ from Bayesian updating? We have to take a stance on that. We would also have to model the information acquisition process by humans. So humans have some private information. They're going to go out into the world and try and acquire some signal about the task at hand. And that's probably going to depend on the AI assessment they observe. If I observe a really confident AI assessment, maybe I spend a little less effort, et cetera. Okay, so we'd have to model that process. We're going to take an approach that is sort of similar in spirit to the structural approach, but it's going to make a minimal set of assumptions. Under these assumptions, we'll have to estimate a sufficient statistic, which is going to turn out to be the probability that a human decision maker correctly classifies a case, conditional on the AI assessment they receive. Under our assumptions, once we estimate the sufficient statistic, we can then generate counterfactual predictions of any counterfactual automation and disclosure policy. It's important to consider when you're designing a collaborative system, the fact that humans are not Bayesian. So we want to be sure we allow for deviations from Bayesian updating, as well as we want to allow for this endogenous response to the disclosure policy. So we want to allow for human effort, for example, to depend on the disclosure policy. Our framework will allow this. So in this paper, it's a framework paper. I'm first going to introduce the sufficient statistic approach to designing human AI collaborations. We'll then implement this in a fact-checking experiment. So the task that we're going to have experimental participants do is going to be to tell us whether or not statements are true or false. And we're going to do this in a two-stage experiment. In stage one, we're going to collect the data required to estimate our sufficient statistic. We're then going to use that sufficient statistic to calculate optimal or approximately optimal policies. In a second stage, we're going to implement the policies that we calculate from stage one in a second stage experiment, totally new participants, and we're going to compare our predictions from stage one with what we observed in the data in the second stage. At the end of the paper, and I'm not going to have much time to talk about this today, we try and understand how, or sort of some different mechanisms that lead to the optimal policy. So we try and address questions like, how do behavioral biases or non-Bayesian updating, how does this impact the performance of humans in our experiment? We're actually trying to characterize the deviations from Bayesian updating that humans exhibit. So we non-parametrically identify the function that humans use to combine their own private information with that of the AI. And then we summarize the deviations of that update function from how a Bayesian would update their beliefs. We also try and quantify the impact of that sort of endogenous effort response I alluded to. We try and quantify the impact of that on the informativeness of the human's own private information. So when humans observe a very confident AI assessment, they exhibit less effort. Does that result in a lower quality signal that they observe from their own research? Okay, as I alluded to, we're going to test this in a fact-checking setting. So humans are going to observe the statement, tell us whether or not it's true or false. We think this is an interesting setting. It's important for limiting the spread of false information. A key challenge in the fact-checking industry is that there are a lot of claims being made in the world, and human fact-checkers only have a limited amount of time to dedicate to actually checking these tasks.
You're talking about decision making, but you're only examining one contribution of the AI, which is evidence. You don't see them as a thinking partner or a decision partner. And the other question is, hallucination is decreasing over time. So is it still as important as it was, let's say, 2 years ago?
Yeah, so I'll tell you exactly what this collaboration looks like, but it's very much going to be in the sort of classifier world. So it's not going to be a generative AI conversation with an AI. It's going to be a numerical signal about the probability that, in fact checking, the probability that a statement is true. And that's what we're going to reveal to participants. I know Sam is going to talk about sort of what you alluded to a little bit, so I'll maybe reserve that for Sam. But that's something that we're actively thinking about. How can we sort of expand the space of interactions that we are considering? But for today, we're only thinking about supervised machine learning. This is a statistical score of the probability.
And how about the other question, which is the hallucinations becoming less of an issue? So is it still as important as those couple of years?
When you say it being important, you mean human AI collaboration, or
no? Just making sure that the collaboration about fact check.
Yeah. So
even that,
yeah,
are more truthful.
Good. So I'm going to tell you what the AI is going to look like. An important requirement is that it's going to be a calibrated signal. Okay, so we would expect some hallucinations or mistakes by the AI, but the important thing is that the score it gives is calibrated. So, for example, if it says there's a 50% chance the statement's true, half the time it's going to be wrong. So that's I think how we would hallucination is. Yeah. Okay. Okay. So I was talking about how productivity of fact checkers is a key challenge. Two leading solutions are fully automated solutions, as well as aggregating the assessments of laypersons. We're going to combine these two approaches in our experiment today. I should also mention that fact checking is very convenient for experimentation. This is an easy task that can be done by pretty much anyone with minimal training. I say easy in that it's easy to explain to the participant, not necessarily easy to get correct, but that makes it sort of convenient. There are also many data sets where there are manually curated labels of ground truth, whether or not the statement is true or false, so we can have a good way to measure. In the interest of time, I'm going to skip the sort of detailed contribution to the literature. There's obviously a huge literature studying human-AI collaboration across many different fields. One other literature I want to highlight is this. We think of this as an early application of some of the learnings from the information design literature to human AI collaboration. Okay, so now I want to introduce the framework that we're going to use to make some progress on this problem. So a little bit of notation. There's going to be a binary state of the world, omega. This corresponds to whether or not a statement is true or false. Every statement or every case is going to receive a classification, A. And today we're going to think about a designer that is trying to maximize the probability that the classification matches the state of the world. All right, so here we're maximizing for classification accuracy. This last bullet is not a restriction to the framework. We could also think about a designer who has different costs of false positives and false negatives. That's easy to swap in. We can also think about including, for example, a cost of delegating to the human. Think about like paying wage. In the experiment today, we're going to optimize for classification accuracy, which is why I introduced it. The designer is going to observe an AI assessment, and it's going to be calibrated. Okay, so this is what I was alluding to earlier. Theta is the AI assessment. It represents the probability a statement is true, conditional on the signal that the AI observes. The designer will observe theta, and they will choose as a function of theta whether or not they want to automate a case. They can just follow the recommendation implied by theta, or they can delegate to a human. If they delegate to a human, they get to pick a disclosure strategy. And a disclosure strategy is just going to be a function from AI assessments to a distribution over signals that we might want to send to the human decision maker. So this set R is going to be the set of signals the designer might want to send to the human decision maker. Could include quantitative statements like the AI says there's a 75% chance the statement's true. Could include qualitative statements like the AI thinks it's likely the statement's true. On the next slide, I'm going to make an assumption, or 2 slides, I'm going to make an assumption that's going to reduce the complexity of this set R that we're going to have to consider. Okay.
How do you define true?
There is the data sets we use have manually curated labels of true or false. So we're going to observe this. Of course, the AI doesn't observe whether or not it's true or false, otherwise it would just report 0 or 1, but they're going to have some signal that's informative of the underlying statement.
Could you give a canonical example of a true statement in this data set?
I have one in a couple slides. They're curated from Wikipedia. So they're things of the nature like, I'm blanking, but like, Kenneth was born in 2003. That would be an example of a statement. I guess that's probably not a true statement. But, who am I? I'll give you an example though. They're a little bit more complicated than that, where they actually require some work to figure out whether or not they're true or false. There are also some compound statements where you have to check several clauses and they all have to be true for the statement.
Something somewhat similar to other, it was discussed advice taking. Like when you study advice taking, they have similar setting in which the advisor is getting a signal about the world and you decide whether you are accepting or not accepting advice, or even since AIs are advising.
Yes, it's a human advisor in this world.
Yes.
Yeah, so
it's similar in the sense that the advisor gets a signal, about the state of the world. And
yeah. So we almost always get this question of like, what is special about AI in this situation? Could this just be another human signal? And the answer is yes, with some caveats. We focus on AI because that's an increasingly important, domain of collaboration and sort of aggregation of different signals. The caveats are, one, the designer has to observe theta, the other signal, for every single case. If it's a human, that can be expensive, so it's not obvious that we would always have access to that other signal. The other caveat is, on the next slide, I'm going to show you that the key assumption we're going to make is going to be, it's going to essentially rely on a conditional independence assumption. And for aggregating multiple human assessments, we might worry that assumption is violated.
I'm actually thinking it might be able to contribute to that literature via your approach.
Yeah, perhaps with those sort of caveats in mind. Yeah, yes.
Can you maybe explain what is this calibrated AI assessment? Like, is this a number or just this?
Yes, so theta is just going to be the AI's assessment of the probability that a statement's true, and it being calibrated means that, for example, when theta is 0.75, means 75% of those statements where it is 0.75 are actually true.
So there's no differentiation between, let's call it false, like for states 1 or state 0, there's no different probabilities of being correct, right? False positive, false negative, same thing.
Well, I mean, it depends on theta, right? Like,
Right.
If theta is 0, then it's confident that the statement is false. It knows it's false with certainty. If theta is 1, it's true with certainty. So theta encodes, information on the full distribution of this binary outcome. Thanks. Okay, One last point I want to make about a disclosure policy is that it's going to be a function from AI assessments to a distribution over signals, because in principle, we want to allow for stochastic policies. That's going to turn out not to matter in our example today. So you can think about a disclosure policy as a function from AI assessments to signals about the AI that we want to send to the humans. Okay, so just to recap, the designer's problem is to design a automation and disclosure policy to maximize the performance of the system. So I'm now going to build up to the key assumption that we're going to make and maintain throughout this paper. That's going to allow us to make some progress on this problem. To build up to this, I want to give an example of one possible micro foundation for the assumption that we're going to maintain to sort of build some intuition of how this works. And I want you to consider a Bayesian decision maker who observes a signal R sent by the designer, and they also observe some private information S. Okay, yes.
Is this like a Bayesian persuasion problem? This AI involved in there?
Exactly, yeah. We're applying some of the tools from information design to try and design an optimal disclosure. Yeah. Okay, good. So throughout the paper, we're going to find X to be the posterior that is induced by the signal R. Okay, so X is just going to represent the share of cases that are true, conditional on receiving a signal R from the designer. And the key assumption we're going to make here is that S and R are independent, conditional on omega and X. Okay, so this is the conditional independence assumption I alluded to during your question. Note that this doesn't, impose that S, the distribution of S does not depend on R. It's only imposing that the distribution of S can only depend on R through the posterior X that is induced. All right, so this still allows for that like endogenous effort response that I alluded to. It turns out under this assumption, we can write the humans or the Bayesian's posterior odds ratio, the likelihood that a statement's true, in the following way. And importantly, you'll notice that this only depends on R through this posterior that is induced of X. All right, so the agent's posterior beliefs only depend on R through X. Turns out that classification accuracy, or the designer's indirect utility, also only depends on R through this posterior X that is induced. This is also going to hold for non-Bayesians, so like Renther agents, for example, who misweight these two terms. And this sort of example here is going to motivate the assumption that we're going to maintain, which is the following. We're going to assume that human accuracy, when a human receives a signal R from the designer, is only going to depend on the signal R through the posterior X that is induced. Okay, so the function v of X, which is just human accuracy, conditional on receiving a signal R that induces a posterior of X, is well defined, is essentially what this assumption is saying. We can unpack this a little bit. There's kind of a couple assumptions nestled within this one. The first is that this assumption rules out any framing effects. It says that only the probabilistic content of the signal matters. The exact wording of the signal doesn't matter under this assumption. This means that we don't have to really think too hard about what that set R is gonna look like. All we really have to care about are the posteriors that we're trying to induce. So in the experiment, we are just going to restrict ourselves to always sending a signal that directly reveals the posterior we're trying to induce. Now I want to highlight that this is almost like certainly false in general. Of course, framing matters, as we could probably know from some of our behavioral colleagues. The way I think about this, though, is we're going to restrict to a class of signals where this assumption seems reasonable, where we're just directly revealing the posterior that we're trying to induce. So we're not going to really be testing this all that strong. The second, maybe more subtle assumption here is that the AI signal is only going to be valuable through the posterior X that we're inducing, and this can be rationalized by, for example, this sort of quasi-Bayesian example with a conditionally independent signal structure. Yeah.
Would you assume the human knows both data and the designer's manipulations of R?
The human does not know data. The human knows the disclosure policy, though that actually doesn't matter. All that matters is that they believe calibration of the signal that they receive. So we're just directly revealing the posterior that we're trying to induce. So they don't have to do the calculation of calculating X. We're just telling them X directly. Yes.
I think if I can follow Roger's comment a little bit better. I was bored enough.
So couldn't I back out the optimal policy given my own behaviors as an agent? In other words, there's a design function that's optimal conditioned on the individual's behaviors.
Yeah.
But if I know my own behaviors, couldn't I back out that optimal policies?
Yeah, so the human here can know the optimal policy. What they don't know is theta. So like one policy could be for any assessment, I'm going to send the same signal. That's like a no disclosure policy. There, even though you know that I'm pulling all the statements together, you can't back out the
theta from the optimal policymaker's decision.
Say the first half of that again.
So could I back out theta from the optimal policymaker's decision? Because the optimal policymaker's decision is a function of theta and my own decision-making parameters.
Yes.
So like, in some sense, if I'm rational, I should be able to back out the theta from the policies adopted by the policy.
Let me give a couple examples in a few slides, and I think it'll be a little bit more clear of how it depends on the disclosure policy of whether or not we're trying to reveal theta or not. You're going to certainly know a distribution of theta, but you might not be able to back out the exact theta, and that would be the designer withholding some information from the human, which they might want to do. I'll give you an example. So just to give a concrete example of what this assumption implies, it implies that the probability a human correctly classifies the case is going to be the same if we tell the human the AI's assessment on this case is 50%. The human's accuracy is going to be the same under that state of the world as under the state of the world where we tell the human there's a 50-50 chance that the AI is certain this case is false or certain this case is true, because both of these induce the same posterior. This is an assumption. It rules out some states of the world we might be in. However, it's a powerful assumption. It allows us to predict the performance of any counterfactual automation or disclosure policy. What's the intuition for this? Well, for an automation policy, it's pretty easy. We automate a case, the AI is calibrated, you know an expectation how it's going to perform. But for a disclosure policy, this is a little bit trickier. What this assumption says, for any signal R we might want to send, all we have to do is calculate the posterior that induces and then look up in V that post. So now let me give you a couple of examples that hopefully make this a little bit clearer. So here's an example. This is simulated data, but this is an example of what V could look like. The x-axis here is going to be the posterior that's induced X. The y-axis is accuracy, human accuracy conditional on the posterior, and the 45-degree lines are the performance implied by full automation. So one policy that we might want to consider is just full disclosure. The designer directly reveals theta to the human decision maker. In this policy, you could certainly back out theta because I'm just telling you what theta is. How do we predict performance? Well, we're just going to integrate V over the marginal distribution of thetas in our data set. You might notice in this V, humans are underperforming automation at the tails when the AI is confident that a signal is true or false. So maybe we want to automate these cases. If we want to consider the performance of this policy where we're automating cases in these orange regions, we're just going to integrate the upper and below of V and the 45-degree lines. Where this assumption really has some value, though, is when we want to think about policies that involve some sort of non-trivial disclosure policy. So here's an example where you wouldn't be able to back out the individual thing. In the orange regions, we're still going to automate these cases. But in this intermediate region, in green, rather than revealing the AI assessment, we're actually not going to reveal the AI assessment. So we're going to do a no disclosure policy where we just send the same signal for all cases in this green range. Then when I see that one signal, I don't know if theta is 0.3 or 0.7. So that's an example where we couldn't back out theta directly, even though we know the strategy. How do we predict performance of this policy? Well, we know how to predict performance in the orange region. In green, all we have to do is calculate the share of cases that are true in this green region, which in this example is 0.5, and then look up V evaluated at 0.5 to get our prediction of performance. Now, why might you want to do this? Well, V doesn't have to be convex. It could be non-convex. For example, if we had a really strong effort response, if we tell people theta is 0.5, they exert a lot of effort. We tell them 0.6, 0.7, they sure can say the AI is good enough, just follow the AI, when there would have been value to them doing their own research. If we have some non-convexity like this, there's potentially value to withholding information. You'll notice that V evaluated at 0.5 here is above the average of V in this range. So that's sort of the intuition for how how this framework works. I hope it's clear the shape of V is very important for determining the optimal policy. If V is convex by Jensen's inequality, we never want to withhold information from the human decision maker in an optimal. If V is not convex, there's potentially some value to withholding information. And if V is ever below the 45-degree lines, there's going to be some value, or there's likely value to automation. Okay, so now let me tell you a little bit about the experiment before we get into some of the empirical results. So as I mentioned, this is going to be a two-stage experiment. In stage one, we're going to collect the data required to estimate our sufficient statistics. So we're going to have 1,500 participants, each a set of 30 statements where the AI is fully revealed to them. This is going to give us the data required to flexibly estimate that function V. We can then use V to calculate optimal and approximately optimal benchmarks. Yeah.
I think this is the right time to ask. So we're informing the human. The human is combining our information with our private information to make a decision. Why not elicit the human's private information and have the AI make the combination and the decision?
Yeah, so we could do that. I'm not gonna have time. So we do an exercise in the paper where we effectively do that. I don't think I'm gonna have time to show those results today. The sort of one caveat is, and this is beyond the scope of our paper, if we do that, the human might be strategic in how they report. So if I have preferences over the eventual outcome, so for example, I'm a pilot flying a plane, and I say, I think we should bank left, and the AI says, I think we should bank right. I might really want us to bank left, and so I might strategically over report my confidence of bank left. I'm not a pilot, so it's probably not the best example, but I hope you get the idea. So that's sort of the caveat that we're not exploring here, but that's certainly a feasible thing to do. When we construct a Bayesian benchmark at the end, that's effectively what we're Okay, in stage two, we're going to recruit new participants, and we're going to implement the policies we calculate in stage one. And we're sort of building up to a comparison between the performance we predict based off of stage one and what we actually observe in the data. All right, and I want to highlight that I think this is holding us to a pretty high bar for evaluating this framework. You can think about this as in stage one, we're estimating a series of counterfactuals. In stage two, we're actually testing those counterfactuals in an experiment, which is oftentimes hard to do sort of economics. All right, so let me tell you a little bit more about the task. Here's your example statement. So the statements are going to come from a data set called Feverus. These are a series of statements that are manually curated from Wikipedia. Here's one such example. I show this example mainly to try and convince you that these are hopefully politically neutral statements. So we don't think something like motivated reasoning is really playing a big role. That's of course an interesting avenue to consider as well. On every statement, the human is going to report a continuous probability assessment of the likelihood that a statement's true. We're going to automatically classify this into a binary, true or false decision. Yes.
So what is it kind of?
0.5. Because we're incentivizing based off of classification accuracy. That's the opposite. Yeah.
So what is the base rate of false true statement? Because that determines the expression.
Well, the incentive determines the threshold. So 65% of statements are true.
Okay.
We incentivize participants using a proper scoring rule, so they should be eliciting their true posterior beliefs. And given that we're incentivizing based on classification accuracy, you should be classifying as true if it's above 0.5, false if it's below 0.5.
65 or something. Usually the optimal classification threshold depends on the prior.
It depends on your posterior, which depends on the prior, but it really if we're incentivizing you based on classification accuracy, if your posterior is above a half, you should classify it as true. Thanks. Okay, we're going to observe effort, which we'll use in sort of the mechanisms that I won't have a lot of time to go into today, through the time that's taken and sort of whether or not you click a Google search button we provide. We have some self-reported measures as well. We're going to construct a AI fact checker using GPT-4o without access to the internet. At the time, it was a leading model. The models have continued to improve. This framework actually gives us a way to think about how the optimal solution will change as models improve, but I'll save that as well for the discussion. We're going to recruit participants from Prolific, and as I mentioned, incentivize it using a proper scoring rule, so they should be according to their true posterior beliefs. Okay, so now we can look at some results. Remember stage one, the goal is to estimate V, use that to calculate optimal and approximately optimal policies. We're going to estimate V using a kernel regression. Let me just jump to the V we estimated. It looks a lot like that first sort of simulated V I showed you at the outset. Again, the x-axis here is going to be the posterior we're inducing. In this case, it's full disclosure in stage one, so you can just think about that as the AI assessment. The y-axis is accuracy conditional on the AI assessment. The first observation is this looks pretty convex. We can't reject that it's convex. This implies in any optimal solution. Whenever we delegate to the human, we're always going to fully reveal the AI assessment. And again, that's what Jen said.
Would it matter if the quality of signal depends on how much effort you put? So for example, if the AI is really confident and I don't put much effort, so those kind of really
Yeah, so we allow for that. The key is that the in that sort of motivating example, so under that micro foundation, the distribution for the human signal has to be independent of R conditional on omega and X. So your effort response can only depend on X. You can't depend on like the wording of R, for example. That's what we're saying. Okay, good. So V is convex. The second observation is we can reject Bayesian updating. V is below the 45-degree lines when the AI is confident either that a statement's false on the left or confident that a statement's true. Why does this reject Bayesian updating? Well, the human has access to the AI assessment. So a Bayesian on average is going to do at least as well as full automation. Here we're doing worse than full automation because we're below 45-degree lines. This also implies there's going to be some benefit from automating. In the appendix, we do some work on trying to like personalize V. There is some predictable heterogeneity. Turns out not to matter a whole lot for both the nature of the optimal policy and the returns to personalization are pretty small in this setting. So this convex V is not just a function of us averaging over a bunch of different types. We tried really hard to look for some non-convexities, and we. Is that a question?
Yeah. In terms of people being non-Bayesian, what do they think about the AI assessment? They know it's calibrated.
They know that it's calibrated, and we
understand what calibrated means.
They demonstrate knowledge or understanding through a comprehension check. It's hard to say exactly why they're not Bayesian. At the end of the paper, we do try and characterize the mistakes that they exhibit. And just to sort of preview, so this is like under response to the AI in some sense, right? Here they're overturning confident AI decisions when they shouldn't.
So that could reflect their beliefs about the quality of the AI's confidence.
Yes. So we decompose this under response into overconfidence in their own private information or AI neglect, which could be, come from them thinking, not believing calibration or thinking that the AI is like less accurate than it actually is. Overconfidence in your own private information explains almost all of this. So humans are more, their posterior beliefs are more sensitive to their own private information relative to a patient. Okay. So now let's go over the policies we're going to test in stage two. We're going to consider optimal policies where automation is allowed, as well as when automation is not allowed. You might think in some situations, possibly including fact checking, we want the human to make the final call. If automation is not allowed because these convex, full disclosure without automation is the optimal policy. If automation is allowed, we still want to do full disclosure when we delegate to the human, but we want to automate these cases where the AI is confident. So this is going to be the optimal policy where we automate cases where the AI is confident, when the AI is uncertain, delegate to the human, fully reveal the AI assessment. We're also going to consider two approximately optimal policies. And we do this because it's interesting that these very simple policies are approximately optimal. More importantly, these policies are going to involve some non-trivial disclosure policies where we're actually coarsening the AI signal. And this is going to be a more out-of-sample test of our framework. Both the optimal policies involve full disclosure, so it's really not that out-of-sample of a test. So what are these approximately optimal policies going to look like? When automation is allowed, it's going to turn out that no disclosure plus automation is approximately optimal. Where we automate cases where the AI is confident and the AI is uncertain, we're going to do a no disclosure. We're not going to reveal anything about the AI assessment in that range. Yeah.
Yeah, Alex, when humans see the evaluation or assessment coming from AI, for example, if it's like 75, how do they understand the number? Does 75% means like among all AI database, 75% of arguments support this versus like 25 disagree with it, or is it actually show AI not being able to evaluate that argument. I mean, what people's belief are when they say number.
Yeah, so I guess that could mean a couple different things. Like one interpretation is similar to Olivia's question of like, do they understand calibration? We test them on that, though, from this graph, you could argue that they don't fully understand calibration, and maybe that's one reason that we see this under response. The other sort of way to interpret that question, if I understand correctly, and please ask again if I don't, is what do we tell them about the like coarsening strategy? Is that what you're getting at? I see. Good. All right, so to restate the question, it's like, what are we telling them about the optimal policy? Under the assumption that we maintain, the actual nature of the optimal policy does not matter for this. All that matters is the posterior that we're inducing. You can think about this as just the designer choosing the distribution of posteriors that we're trying to induce, subject to a technical constraint that the distribution of posteriors has to be a mean preserving contraction of the original distribution of AI signals, because we can't add information. We can only withhold information. So we try and keep the experiment about the information that we're providing, and we try not to add too much framing. So we don't explain like this is how we got to this AI assessment. We just reveal the posteriors directly. So that's what we do in the experiment. Yeah. So we just like in say should we just say like this is a new AI tool, and it has it's going to give you a different distribution of AI, and we sort of describe a little bit what that distribution looks like just to make it natural, but we don't say that this is like a coarsening of the original AI signal. Yeah.
Is there any room for maybe a potential explanation around like subjective probability? The fact that individuals might see like a 99, like you tell them that something has like a 1% chance of occurring, right? And they feel or they behave as if that risk is greater than that 1%, and therefore they're essentially hedging. Like the AI says that it's 98% likely to be true, and they think, oh, maybe this is 1%. I guess how that is that potentially detectable within this, separable from?
So I think that would be, I think it's very related to Olivia's question about like calibration. Do you believe that, or do you act as if 99% is actually 99%? I think if that were really driving the results, we would see a lot of AI neglect. And what when we do this decomposition, we find that overconfidence in your own private information is the main bias. Again, I'm not going to have time to really go into that today, unfortunately, but yeah, I'm happy to chat more offline, but that's perhaps a little bit beyond the scope of the thing. Thanks. Okay. So approximately optimal when automation is allowed is no disclosure plus automation. When automation is not allowed, it's going to turn out a stoplight policy is approximately optimal. And this policy will partition the space of AI assessments into 3 intervals. Then each interval will do another disclosure policy. You can think about this as saying like, likely false, uncertain, likely true, or red, yellow, green, hence the stoplight. But the keys we're only going to send these 3 signals. And then of course we'll have a human-only benchmark, disclosure plus no automation. All right, for each of these different policies, we can generate a quantitative prediction of performance using this framework. Rather than focusing on the quantitative predictions, I want to highlight a few qualitative predictions. We're going to predict that both the human and the AI add value. The humans add value because the optimal policy, full disclosure plus automation, outperforms full automation, or we predict that it'll outperform full automation. And remember, this optimal policy involves humans, so humans have some value here. The AI has value because we predict that the optimal policy with automation is going to outperform the optimal policy without automation.
So Alex, I'm sorry if I missed it. There are potentially infinitely many disclosure policies.
That's right.
How did you restrict that space? And the corollary question is, if you relax that restriction, would these results be robust?
So we restrict. So let me answer this in 2 parts. Under the assumption we're not restricting the disclosure policy. So there's an infinite number of policies one could consider, and under this assumption, we're able to find the optimal. Now, this assumption has some restrictions. So like framing doesn't matter, for example. If we sort of relax that and thought about, humans in the wild, they of course respond to framing. So if I say like, there's a 99% chance the statement's true, you should really classify this statement as true. that would probably be different than the results we see here. We're restricting to the class where we're just directly revealing the number because we're not super interested in this.
Could a disclosure policy be something like mine? Like converting the probabilities?
In this model, humans. So we're
So like in other words, I disclose that AI is,
you exaggerate, for example.
yeah.
Yeah, exactly. That is something you could do in this model, though. Remember, only the probabilistic content of the signal matters. So humans would do that update, and they would adjust for this distortion, for example. In practice, whether or not people would respond to that and sort of how long it would take them to respond is an empirical question, and it's an interesting one, but it's not what we're studying. Okay. The second prediction is that the value of direct human-AI collaboration is going to depend on whether or not automation is allowed. If automation is allowed, there's very little value of direct human-AI collaboration. And then, of course, we're going to predict these simple disclosure policies are approximately optimal. Okay. In the interest of time, I've only got about 4 minutes. I'm going to quickly go through the second stage results before I wrap up. So here I'm going to show you the results of the second stage. In blue for each of the 5 policies, I'm going to show you the quantitative prediction of performance based off stage 1. In orange, I'm going to show you another prediction of performance based off phase 2. You can ignore orange for this talk. And in green, I'm going to show you the actual performance of the humans in stage 2. So let's compare blue to green. In the human-only arm, as we'd expect, performance is the worst. In terms of quantitative predictions, this is going to be our biggest miss for sort of subtle reasons that I'm happy to go into sort of after the talk. If we move on to policies where automation is not allowed, as we'd expect, performance increases. And also, as we'd expect, the performance of or we can't reject that the performance of the approximately optimal policy is different than that of the optimal policy. If we move on to policies where automation is allowed, again, as we'd expect, performance increases. And again, we can't reject that the approximately optimal policy is equal to that of the optimal policy. So my takeaway from this figure, first, that there's a lot of value of designing an optimal collaboration. Performance goes up by a lot. But also, perhaps more importantly, if you think back to all of those qualitative predictions that I made, and a lot of the quantitative ones are all borne out in this data, which gives me some confidence that we're doing a decent job of designing an optimal policy in this. We can kick the tires a little bit more directly by using these by using the approximately optimal policies that involve non-trivial disclosure policies. And to do this, let's just look at the orange circles here, which correspond to the stoplight policy. Remember, the key assumption that we're going to make is that the performance of any signal that we send is only going to depend on the posterior that we're inducing. So in stoplight, we're effectively sending likely false and certain likely true. When I'm plotting in these points is performance conditional on receiving each signal, and we see that they're pretty close to this V of X curve, which is consistent with that assumption holding. I don't have time to go through the mechanisms in detail. I'd love to talk about it over dinner or the coffee break, but this is where we address sort of this like under AI neglect versus overconfidence by the human, for example, as well as trying to quantify the impact of this endogenous effort response on the informativeness of the humans of the project. Okay, so to wrap up, the objective here was to introduce a framework where we contractually solve for an optimal automation and disclosure policy. On the methodology front, it seems like this framework does a pretty good job of predicting treatment effects and performance in this setting. On the substantive front, we find that full disclosure is always optimal. There's a lot of gains from automating cases where the AI is confident. This comes from the humans being overconfident in their own private information. The value of direct collaboration is modest. We saw this by noticing that the no disclosure plus automation policies is approximately optimal. And finally, I didn't have time to go into this, but the optimal policy achieves the Bayesian part. So this sort of ex post combination that you so thank you all. Yeah, Olivia, a question.
In terms of humans being overconfident, I'm wondering if you also elicit beliefs about the final judgment. Like when you test in the second experiment these different policies, how do humans reflect on their own performance in the non-complete automation settings?
What do you mean by reflect on their own performance?
I guess like one version of, so you could say, these people are, you test that people are overconfident in their own private information. How confident are they in their final judgments?
So we're listed a probability assessment, and so that contains a confidence measure, and we see that they are they're not calibrated, so they're more likely to report something close to 0, close to 1, which is reflective of this overconfidence. Okay. Is that what you're getting at?
In their posteriors.
Yes.
And that doesn't vary across the different policies, approximately optimal, optimal.
So in that decomposition, we make an assumption that private information is, we make an assumption that the update function is structural and it's the same across different across the different policies. We also make the stronger assumption that we make the assumption that your private information is IAD conditional on state of the world data in effort. So the only reason that could change across arms is because. Thank you.
Awesome. Thank you all. Thank you for having me. It's great to be here. Alex did a fantastic job with that paper. So like the first couple slides of this, I'm going to go through pretty quick. We'll certainly finish with maybe an extra minute or two for coffee because we started a few minutes early too. My name is Sam Goldberg. I'm an assistant professor at Stanford Graduate School of Business. And I'm discussing Alex's paper here, Designing Human AI Collaboration, a Sufficient-Statistic Approach. Okay, so this paper in one slide, the question here is which cases to automate, which to delegate, and what to tell the human if we do want to give them information, okay? So we're thinking about a setting where we have, I think Alex said it correctly, it's not, you should really think of this as more of like a ML system than necessarily like a modern AI system. It's a binary recommendation. The human's trying to make a classification decision. When do we tell them the recommendation? When do we hide that recommendation? How do we communicate it? And when do we not tell them at all and let the machine make the decision? Okay, that's sort of the question. That's sort of the series of questions we're going to answer today. Why is this hard? Well, if you start to think about this problem, there's essentially an infinite number of ways I can give you that information or switch between automation and delegation. And humans are going to respond endogenously based on what information you give them, right? So both they're going to choose how to exert effort, they're going to update in sort of potentially non-Bayesian ways. And so because of both of those, a very high dimension problem space and a very complicated human response, experiments and sort of structural approaches are going to be really difficult here. I think Alex sort of nailed that point in his conversation. The key insight that they're going to come at this with is that there's actually sort of one function, which is essentially that the probability that the human will get the classification correct, conditional on the AI signal, right? So conditional on whatever posterior they hold, that's going to pin down the optimal policy here. They're going to estimate, show that you can estimate this function once under a sort of a full disclosure regime, and then use that to predict accuracy under any sort of counterfactual policy. And basically, this insight is going to come almost directly from sort of a long-running theory literature and information design. They're then going to sort of use an experimented algorithm. So ultimately, I should be clear, this is a fantastic paper. It's extremely tight and it's a joy to read, though maybe a little dense. And so this discussion is mostly going to be talking about how great this paper is, as well as sort of the boundary conditions. And so we can start to think of what we should be working on next here. Okay. All right. So again, this is what I'm going to go through pretty quick. So why is V sufficient? What is the state of this game? So AI is going to produce some sort of assessment theta, and the designer is going to choose what to tell the human. There's one critical assumption here, and this is what we're going to talk most about in this discussion here, which is that the human's accuracy, so their posterior probability of getting the classification correct, given the signal of given the signal that the designer is giving them, only depends sort of on that posterior. Okay, so the probability that they get this correct as a function of R is totally encompassed by their posterior belief about what the answer to this classification problem is. What that means is it's not going to depend on how X was constructed. It's going to rule out some things like framing effects. Alex mentioned those explicitly. And it's not really going to depend on the distribution of theta behind that signal. Okay, so it greatly simplifies the problem space here, right? Essentially, what this means is that we're in this sort of Bayesian persuasion world, where what the designer has to do is induce a posterior over the sort of classification problem afterwards, which means we know G, we're choosing G, that's our optimization problem. We just need to solve and estimate that V, right? That's what That's essentially what this paper is about. And once we have that V, we can kind of think through any G and what posterior that induces to design our problem. Okay, so what do they tend to find? And this is sort of a reproduction of the exact figure that Alex showed you, and he did a better job explaining this than I ever could. But essentially, what they find is V is convex, and what you should know from the Bayesian persuasion literature is that if V is convex, we fully reveal. Okay, that's actually pretty intuitive because if you tried to not reveal, right, if you just told them 0.5, you'd end up lower than you would if you told them 0.33 and 0.69, right? You take the convex, the concave closure, convex closure, right? What they also find is that the automation is better sometimes than the human, right? And so you see that in this nice graph where that dotted line is above the solid line. Two forces that they focus on that can break convexity, so convexity is not a given here, are going to be effort crowd out. So I get a signal from the AI, so I just sort of take it and don't invest the effort to learn. And then the other could be, some version of overconfidence. In this case, neither of them is going to be strong enough. And so indeed, we do find this. Okay. Headline results, automation is valuable. Humans add value. Collaboration, isn't particularly valuable here. And we'll talk a little bit about why. Simple policies suffice. So that stoplight is actually a pretty good policy. And essentially all of their qualitative predictions are confirmed. And they show that sort of overconfidence is one of the key sort of behavioral things that's driving the AI to be slightly better than the human in some instances. Okay, so now I want to talk through sort of 3 points. Two are more related to assumption one, and the first is related to sort of unpacking why disclosure is not going to be super valuable in this setting, right? And so when do we want to disclose? So when do we want the human and AI to collaborate, right? So that's exactly in that region, right? In that middle of that U, where we're above the 45-degree lines, right? But we're below, but they're cut off on the ends by the 45s, right? So that's the
Smiley face.
the smiley face, right? Yeah. So where do we collaborate is right here, right? This is where we want to share information, okay? So when is this particularly valuable? Well, it's particularly valuable when V is strongly curved. So when, we get a lot higher from here, higher from here by giving them this information. And when X has meaningful variance, okay? So when we're far apart over here from here, right? And so in their setting, what they find is V is actually really flat in that area, right? So there's not a lot of variance, and V is not particularly strongly curved in this region. And so that's why we don't see much value for collaboration. But that doesn't mean that that's not true in other settings, right? And so collaboration could be very valuable in other settings. And in fact, if you go back to their other paper in radiology, right, where this is a setting where radiologists are given an AI recommendation of whether or not the image has cancer, essentially. The intuition here is that the value of the AI recommendation, the convexity of that curve, should get more valuable as the information sources are divergent. So in the radiology setting, the radiologists get the image and they get the case. They get the deconstructed information in terms of like what the doctor wrote down, and the AI only sees the image. Okay, that's a setting where the signals are very uncorrelated, which means that the collaboration value should be high. And indeed, they do find that sort of collaboration could be valuable here, but unfortunately, these experts actually neglect the AI, so they choose to ignore the AI more than these people do in this experiment. And so the question that I have to ask, the question that comes to mind here, and one sort of question for you guys is sort of, when we think about the context where collaboration might be valuable, how correlated are those valuable places with these behavioral biases that go against the collaboration, right? So this is a place where collaboration should be valuable, but what happens is the experts don't trust the AI, they neglect it, and so it ends up not being particularly valuable. How often is that the case? Is that always going to be the case? When will it not be, right? Second thing I want to do is think a little bit about this assumption one, okay? So just to restate, so the human accuracy depends on the AI signal only through that posterior mean. What this means is that, when the signals are correlated, they can only be correlated through the true states. So there's two there's sort of a demand side reason and a supply side reason we think that might break. And we've talked a lot about the demand side reason, I think, in this conversation, which is if the humans sort of absorbing some of the AI signal and then potentially using that to invest effort selectively. So an example would be in a modern LLM system when you're having a conversation with an AI and there's some sort of reasoning being explained to you, and you decide, okay, I believe this reasoning, but I don't believe this reasoning, and then you sort of adopt different pieces of information rather than the whole thing, and that changes your posterior beliefs. That's a reason this is going to break. This is not a problem in their setting, right? Because they have a binary signal. There is no conversation, and they're not complicated, right? And so it's sort of an extra. This is sort of when we think about a boundary condition here, this could be an issue. The second reason on the supply side is that the AI may be absorbing some of the human signal, right? And so there's some evidence of this, at least anecdotally, that these AI systems are personalized to you, so they know your preferences to some extent, and that may change the information they give you. The kind of colloquial term for this is sycophancy, right? So the AI tells you that you're right, even though it sort of thinks that you might be wrong, or tilts its information into your confirmation bias, right? And again, so the experiment completely avoids both of these, but these are relative boundary conditions. And I think that the supply side is particularly interesting and particularly relevant here, because what that means to some extent is that in their world, they're designing a system, they're designing a collaboration mechanism conditional on that distribution of thetas, that F, right? But in the real world, that F is potentially endogenous. And in particular, it is by design endogenous in these LLM systems. We use things like reinforcement learning with human feedback in order to personalize these things and tilt answers towards what people want to hear. There are two consequences from that. So first, these sort of sycophantic aspects of theta, these endogenous shifts of F, could completely change the shape of V and potentially make them concave in certain regions. But worse, V is actually no longer a sufficient statistic, right? Because we do break that assumption. And so ultimately what that means is that if you put all this together, what I would push us to do, and I know that they're thinking about this in a follow-up paper, is how do we take this to sort of the more practical, real-world, widely deployed LLM systems that we see today? In their world, like experiment versus real world here. So in the real world, we have better AI. So the questions where we want to collaborate may be changing. Automation regions may be expanding. Delegated cases are fewer but harder. Where do we find the most value and how do the biases interact with that? Second, going back to the first comment on assumption one, LLMs can explain themselves. That's going to shift shift the correlation structure between the human signals and the LLM signals, which is going to cause some problems, I think, for them. And then ultimately, I would argue that data is certainly a more complicated setting is often not exogenous to the user signal. And what this means is that you kind of want to think about the joint design problem of the training objective and the disclosure policy. Other extensions, these are sort of ad hoc. You could certainly think about asymmetric losses. I think Alex has already thought about that. We talked strategic environment. We also discussed, right? So humans may not report their signal truthfully under different sort of design games. And of course, you could go to multi-run communication if you wanted to think through that sort of endogenous information. Anyway. Excellent paper, sidesteps sort of the structural modeling of human cognition, which is an amazing simplification that I think is pretty credible in their setting, to be clear. They can validate it out of sample in a lab, and it's super policy relevant. I think the main questions I have are just sort of, what do we do next, and how do we continue pushing on this problem? Because I think a lot of major AI systems are sort of deployed in different ways than these sort of binary signals at this point. Thank you.
Yeah, thank you very much. I agree with almost everything that you said. When we think about like which settings we really think this is going to be useful, I agree it's when the human and the AI are looking at sort of different parts of the information space or like different pieces of information. More generally, explanations likely would not. Would sort of break this assumption. So that is a boundary condition. Hope to have more to say on that in the future, but currently don't have a ton to say there. But totally fair point. The one point I would sort of offer thoughts on, maybe not disagree, is that as the AI gets better, it's going to change two things. One is well captured in the model, data is going to get more spread out, which we can handle. If the correlation structure changes for some of the reasons you discussed, that would be a little bit more problematic. That's of course something that, if we were to deploy something like this, we want to continuously re-estimate something we would impact. But yeah, thanks for the discussion. Great points.
Thank you.